This lecture is going to be about limits. The idea with limits is what's happening with your function as you're plugging in numbers for x, getting closer and closer to a certain other number. So if I have, say, a graph of the function, and let's give myself a graph, y equals f of x, and I care about this point. 1, 2, 3, 4. That's a 5, and that looks like a 3. Okay. Now, as I plug in numbers closer and closer to 5, the value of my function will get closer and closer to 3. Here, if I plug in something a little bit smaller than 5, it'll spit out something a little smaller than 3. If I stick in something a little bit bigger than 5, it'll spit out something a little bit bigger than 3. And so as I get closer and closer to the 5, the values of my function will get closer and closer to the 3. So I can say the limit as x approaches 5 of f of x is equal to 3. Now, if my function is nice and continuous, then the value of the function will equal the limit. So let me write that out. If f of x is continuous at x equals, let's just be generic and call it a, then the limit as x approaches a of your function is equal to actually what f of a is, which means I can plug it in. And what does continuous mean? Continuous means you can draw the graph without lifting your pencil. Doesn't matter if it's all spiky, but I can draw it without lifting my pen, whatever. So one way is to look at the picture and just find the value of the function. So what if there is a hole in your graph? Let's say your function looks something like that. And this is what 1, 2, 3, that's a 4, that looks like a 2. Now with limits, we don't care what actually happens at 4. This function is not defined at 4. We don't care. If I were to fill in the hole, then my limit as I approach 4 would be 2. So even though there's a hole there, I can say the limit as x approaches 4 of f of x is equal to 2. Because as I approach it from the left or the right, I'm still getting the same value. So the limit here is 2. Now, what if there's not a hole? What if it's not a hole? What if it's not continuous? So what if we have this scenario? I draw like this. I've got a hole and a jump. And this goes off and does its thing. And let's see, we'll call that 5. This one's 2. This one's 4. So as I approach 5 from the negative side, things smaller than 5, my function is getting closer and closer to 2. So this chunk of the graph, the dot is at 2. So I can say the limit as x approaches 5 from the negative side, things smaller than 5, is equal to 2. But if I come from the positive side, I have a different branch. This branch ends at 4. So I can say the limit as x approaches 5 from the positive side of my function is 4. Now since these guys are not equal, we'll say that the limit as x approaches 5 does not exist. Though typically I'll say D and E because I'm too lazy to write out all that. So looking at pictures, you just figure out what the value of the function is if you can, and if it's broken, you can do a left one or a right one. If it's not broken and I say, let's see what I'll call that. Let's say I ask you what the limit as, this is 3, x approaches 3 from the positive side of my function equals, well, the function is continuous at 3. I don't care if I come at it from the left or the right. I'm going to get the same answer. And it sure looks like my answer is 1.5 or 1.5. So sided limits only come up if you actually have a break in your graph, or maybe if you're looking at a piecewise defined function and it has something weird going in that on the left and the right of a point. Okay. Now, what if you don't have the graph? What if you have the function? Let's say I want to look at the limit as x approaches 3 of x plus 2 over x minus 2. Now, this nice pretty function, only place it's going to be weird is at 2, like we learned on Tuesday in class. Sticking a 3 in here, no problem. The function is going to be continuous and beautiful everywhere except 2. So I can just plug in. That's all I have to do. So the limit, plug in, Megan. 3 plus 2 over 3 minus 2. So I get 5 over 1. The limit is 5. So the first thing you want to do if you see something in this form is plug it in. If you get something normal, that's your answer. If you get something weird, you might have to jiggle it. Now, what do I mean by that? Let's say I have the limit as x approaches 3 again, but this time I have x minus 3 over x squared minus 9. Now we know that this function is going to be screwy when the bottom is 0. So that means that if I factor x squared minus 9, I'll get x minus 3, x plus 3. So this function is going to be screwy at 3 and negative 3. And 3 is the spot I'm looking at. If I try to plug in, just straight plug in, I will get a 0 on top and a 0 on bottom. Now if I have a 0 on top and a 0 on bottom, that means I should be able to cancel something. Because 0 means you've got a factor in there that's giving you the 0. So I'm going to factor this. On top I have x minus 3. On the bottom I've got x minus 3, x plus 3. So the offending factor, which is giving me a 0, is this x minus 3 term. So now I can plug into the leftovers. I have a 1 on top, 3 plus 3 on the bottom. My answer is 1/6. So the bottom line, the first thing you do, plug it in. If it's normal, that's your answer. If it's funky, I don't know why I have 1, because I'm not going to do any, I did 2. If it's funky, that means you have to jiggle it. Jiggle, factor, and cancel. And hopefully the thing that's bugging you the thing that's giving you a 0 on the bottom will cancel out, and you'll be able to plug into the leftovers. So those are the two ways we look at functions, limits. We're going to look at graphs, or we look at the function itself and try to factor it and cancel out if it's giving us a 0. Then we'll talk about limits going to infinity on another day. That's all. Thank you.